This unit is about binomial probability distributions. In your textbook, it talks a lot about these in the chapter 9. For binomial probability distributions, it needs to satisfy the following conditions. So we need to have n independent trials. So we're like rolling a dice, for example, where the dice doesn't have any memory of what happened in the past. There can only be two possible outcomes, either a success or a failure, and the probability for success is fixed at each trial, p, and probability of failure is the complement of that. So for example, if p was 0.1, q would be 0.9. So let's have a look first before we do anything, just to make sure we know what is and isn't a binomial probability distribution. So the first one, how many times a head comes up from n flips of a fair coin? Correction, from 10 flips of a fair coin. So the number of trials is 10. So probability of success would be getting heads. Uh, 0.5, which is the p-value. Q would be 0.5. Looks good. Example of something not binomial, how many times the teams win? Okay, don't know what n is, don't know what p is, don't know what q is. Doesn't seem like a binomial probability. Okay, number of boys in a 10-child family. We're going to have 10 trials. Success is a boy, which would be, again, a half. Failure would be getting a girl. Okay, it doesn't mean necessarily success and failure, it's just the thing that we're interested in. 0.5. Okay, so it looks good. Binomial probability distribution. Not binomial would be the possible outcomes of rolling a die 7 times. So n equals 7, but there's too many outcomes. We only want 2 outcomes. Here we've got 6 outcomes, which we don't want. Number of faulty parts from an assembly of 150 faulty parts, where the likelihood of a fault is 0.02. In this instance, doing 150 trials, probability of success. So in this case, success is a fault. Probability of that success is 0.02. Probability of failure is 0.98. Okay, so the failure in this scenario is actually a good part. So that's all good. I've got NP and Q. Number of aces dealt in the first 5 cards of the deck without replacement. So n equals 5, but the problem I get to is P. So I think, okay, probability of getting an ace, 4 on 52, but it's not fixed for each trial. In the second trial, the probability won't be 4 on 52. It'll either be 3 on 51 or 4 on 51, depending on whether we've got an ace in that first card. Okay, so that's the reason why that's not binomial. Okay, but all of these definitely are binomial. So I've actually done binomial probability already, okay, but just under a different name, just using tree diagrams. So if you recall the scenario with the 3 balls taken from a bag containing 6 blue and 4 yellow with replacement. Okay, with replacement is crucial here because that means that these probabilities stay constant all the way through. We wanted to use the tree diagram to calculate the probability of selecting exactly 2 balls. So the way we went about this was did our tree diagram, identified how many different ways we get 2 balls, and then we added these 3 together to get my 432 on 1000. Okay, but some of you rightly identified that this is quite tedious. Okay, we see that this 144 on 1000 is always the same. Okay, why can't we just find that and multiply it by 3? Well, that sounds like a great idea. How did we find this? Well, all of these probabilities as well are the same, just in different orders. So what we really should have done is found that probability of success, so getting the blue ball, was 6/10. probability of failure was 4 over 10. So we should have just multiplied the success by failure, and then multiply that all by 3 for the 3 different outcomes that there are. Okay, so we were choosing 3 balls, so we can be helped out even more in finding where that 3 different combinations are, rather than looking at a tree diagram. What we can do is have a look at all these different outcomes that we had, so 0, 1, 2, or 3 blue balls. 0 occurred once, okay, there it is. 1 blue ball occurred 3 times. 2 blue balls occurred 3 times. And 3 blue balls occurred just once. So if we look at how many different combinations of getting 0, 1, 2, or 3 balls, we can see that it lines up exactly with this third row of the Pascal's triangle. Okay, so that'll be extremely helpful rather than having to draw this tree diagram when we're going down here, perhaps choosing 6 balls and seeing how many different ways we could get, say, 3 blue balls. Okay, there's 20 different combinations. We don't want to have to draw these massive tree diagrams. Okay, so this is the idea, this is the sort of theory behind it. We won't use Pascal's triangle, we'll use combinations to get these numbers, okay, a special function that we'll use on the calculator, but this is the general idea behind what we're going to do. So binomial probability formula, we all love a formula. Probability of attaining X successes from N trials in any order, where P is the probability of success and Q is the probability of failure, is given by that formula. So it looks like a pretty nasty formula, but we'll get through it. So let's have a look at it in practice. So use binomial probability formula to calculate that same probability we had before, selecting exactly 2 blue balls when choosing 3 from a drawer containing 6 blue and 4 yellow. So my success, I always need to define what success is a blue ball. My probability of success is 6 on 10. My probability of failure, Q, is 4 on 10. And now I'll have a go at writing this formula. So I want the probability that my number of blue balls is exactly 2 will be NCX. So my number of trials, I was selecting 3 blue balls altogether. So this will be 3C2, because I'm after 2 successes. So this 3 is like a power on the left hand side, and the 2 is a subscript down below. So probability of success raised to the power of how many successes I wanted. So 6 on 10 to the power 2. So this 2 here implies that my lowercase x is 2. Multiplied by probability of failure to the power n minus x. So 3 minus 2. Right, the way we get this 3C2 on our calculators is in options. We'll go across to where it says probability, and we're going to use this C. So if I type 3C2, it might look different on your calculator, will give me 3. So that's given me how many different ways I could have selected the 2 blue balls. So I'll put the 3 here. I always recommend just doing 3C2 to get a feel for it, and 4 on 10 to the power 1. Okay, so you can either use that 3 or put everything in at once. It's up to you. Okay, to the power 1, don't need to write that. There you go, 0.432. And we can make that into a fraction, 54 on 125, which I think is the same as we got previously. Looks good. Okay, so that's the idea of binomial probability formula. We use it when we don't care about what order they come. If I have a question that says find the probability of obtaining 2 blue balls and then a yellow ball in that order, so an order is specified, I can't use that formula. Okay, if I wanted to do this problem, probability of blue, then yellow, I would just have to multiply those probabilities together to just get that one outcome. Okay, so essentially just looking at, if you look at your tree diagram, just looking at this one path on the tree diagram, blue, blue, yellow, this one, to get my 144 on 1,000. When you learn a new trick, it's really important to know when you can and can't use that new trick. All right, we'll have a look at just some other examples just to further familiarize yourself with it. Find the probability of obtaining no blue balls. So again, probability of success is 6 on 10. I'll write it as 0.6 this time. Probability of failure, 0.4. Number of trials is 3. I'm looking for probability of obtaining no blue balls, so when lowercase x equals 0. So 3C0, 6 on 10 to the power 0, and 4 on 10 to the power 3 minus 0. Okay, when we look at some of these, like 3C0, okay, we notice that that's 1, because there's only one way that we can get no blue balls altogether. Okay, 6 on 10 to the power 0, I'll type this in, but I really shouldn't because I know that's just going to be 1 anyway. And multiplied by 4 on 10, all cubed. Okay, it's me 0.064. Okay, pretty unlikely to happen. Okay, what about probability of obtaining all blue balls? So again, same success, same failure, same number of trials, but I want all blue balls. So that'll be 3C3, 0.6 to the power 3, 0.4 to the power 0, or 3 minus 3 if you want to do it properly. Again, enter calculator. Interested to see what 3C3 is. How many different ways can I get all blue balls? Oh, only one. Okay, and I can go crazy. So 0.216 for all blue balls. Okay, finally, find the probability of obtaining at least one blue ball. So a few different ways you could go about doing this. Okay, we could have the same P, the same Q, the same N, and do x equals 1, x equals 2, x equals 3. It would be a lot of work. Okay, alternatively, I could just know that probability of obtaining at least one new blue ball is the same as all the probabilities except getting 0, which I've already calculated previously. Okay, so there we go. So when you do these problems, I'd set it out like this part A example, where I'd write what success is, write probability of success and failure, write the number of trials, write what the x value is, okay, in this case x equals 2, and substitute it into the formula. So you get a lot of practice with this. You can also check your solutions with a calculator. I'll put some steps here of how to do it, but I'll just quickly show you how I could check this first example. So I go into my stat mode. It's a distribution, a binomial distribution, and I want a binomial probability. So I change this to variable. I wanted 2 successes in 3 trials, and my probability of success is 6 on 10. And I'll go down and execute, and I'll get my probability of 0.432. Now you can use this to check, but in the exam you'll have to do it by hand. Okay, there's some more detailed instructions here if you're really keen. Otherwise, get into those questions.